Hi, this is Combined Gas Law Part 2. So in Part 1, we kind of looked at what the conceptual basis why there is a combined gas law, so that again, it's easier to understand. This time, we will take a look at the mathematical foundation of it. So you have to remember that Boyle's law kind of is formulated like this, where if you take the pressure of a gas and take its volume, multiply them, and then somehow you make a change. That's why it's now P1 instead of P2. You make a change in the pressure, so therefore the volume also changes. It would so happen that if you multiply P1 and V1 and multiply P2 and V2, they will be equal to each other. So the Boyle's law is formulated like this. While if you have the Charles law, it's not a multiplication of the two, but it's kind of a division. If you multiply the volume by the temperature of the first state, that's equal to the volume and the temperature of the second state, and also Gay-Lussac's law, but now you're dealing with pressure and temperature. Now, again, the goal of a combined gas law is kind of combine, merge all of these three laws. So how do we kind of look at it? Well, um, if you if you are observant, you kind of see that all the P1, so P1 appears here, is in the numerator. See? P1 is also in the numerator here on the left side. And all the V1s are in the numerator on the left side, right? And all the T1 are in the denominator on the left side. So therefore, I can say, okay, P1 should be in the left side, V1 should be in the left side, while T1 should be in the left side, but in the denominator. Okay, again, I know this is not quite mathematical, but again, I feel like it's more conceptual and it's easy to understand. If you look at this, P1 here is in the numerator. P1 is also in the numerator. Here, there's no P1. So, and then V1 here is in the numerator. V1 here is in the numerator. But T1 is in the denominator here. And T1 is the denominator. So if we merge them, we kind of end up with this. Right? That's in the left side. If you look at the right side, well, it's easy. P2s, the P2s are in the numerator. The V2s are in the numerator. While the T2s are in the denominator. So it's as simple as that. Now you have kind of combined all of the basic laws, Boyle's law, Charles' law, and Gay-Lussac's law into this law. And this law is again the combined gas law. And guess what? Because if you notice here, P1 and V1 and T1 can change. They can become P2, V2, and T2. So therefore, because you are now looking at the relationship of P versus V versus T, you're looking at a three-way relationship, unlike in Boyle's law, Charles's law, and Gay-Lussac's law, where you are only looking at the relationship of two variables. In this case, you're looking at the interrelationships of the three variables. And again, because there are four variables, in this case, you are looking at P, V, and T, but you are keeping N constant. Okay, so this is the formula for the combined gas law. P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. Okay, so now let's take a look at an example. And again, just so that it kind of is cemented in our minds, let's just kind of rewrite this. That again, in the combined gas law, you're looking at the relationship between pressure, volume, and temperature when the number of particles is kept constant. Okay, so let us have a sample problem. So the sample problem is this. What if you have a gas and the pressure of that gas is, let's say, 2 atm. I could have this in Pascal, but let me just choose 2 atm. And then what if the volume is, let's say, 3 liters? And then the temperature is, let's say, 200 Kelvin. Now, please take note that when you're dealing with this kind of problem, the temperature must be in Kelvin. So for this case, I will not make it difficult for you. We will use Kelvin because again, we are still kind of looking at how this formula works. Okay. And then let's say once you have that, what if you increase the pressure such that the pressure is now 6 atm, and then you kind of decrease the volume into 1.5 liters. Now the question is, what will be your temperature 2? Okay, very simple. you have a container. That container of gas, the gas inside that container has a pressure of 2 atm, and then it has a volume of 3 liters and has a temperature of 200 Kelvin. What if the pressure of that container changes to 6 atm, and then the container kind of maybe there's a mechanism for it to change volume, or it contracts like a syringe, but the point is the volume changed to 1.5 liters. Question, what will be your temperature too? So again, very easy. You just have to, I know some of you are very good at this already. So again, you just simply look at the formula for the combined gas law and say, hey, we have, this is a given, that's a given, that's a given, that's a given, that's a given, and this is what is asked, which is temperature 2. So therefore, it should be pretty straightforward. So with some manipulation, this would be, it would be T2 would now be equivalent to P2 V2 divided by times T1 divided by P1 V1, right? And again, I hope you can kind of piece one and one together and become, so that it becomes two, so you can kind of track how this happens, how this becomes like that. Okay, let me double check if I made any mistake. Nope, that's the correct formula. So T2 is equal to P2V2 times T1 divided by P1 over V1. Okay, so let us erase that and kind of do the calculation. So again, if I remember, T2 will be P2V2 times T1 divided by P1 times V1. Okay, and all you got to do is obviously substitute the values. So you have 2 atm times the volume. Again, you're sorry, not 2 atm. I was looking at the wrong one. It should be P2, so I should not be looking at P1. I should be looking at P2 here. So that's my bad. So that's 6 atm times V2 is 1.5 liters times temperature 1. Remember, this is not temperature 2, but temperature 1 is 200 Kelvin. Then all I got to do is, again, P1 is 2 atm and V1 is 3 liters. Okay? Then all I got to do is, again, calculate that. And remember that canceling the units is important. It tells you if your calculation is correct. So in this case, I see that ATM is divided by ATM, so they cancel out. Liters divided by liters, it gets canceled out. So guess what? When I do my calculations, what happens? The only thing that is remaining there in terms of the unit is Kelvin. And since I'm calculating for temperature, that's good because I want my answer to be in Kelvin. Otherwise, if it ends up not in Kelvin, that means something is wrong with my formula. Maybe I messed up something when I manipulated the formula. But that's the idea. So now you have this, which would be probably what? That would probably be 300 Kelvin. Because let me see, if 6 divided by 3, if I reduce that, that becomes 2, right? So if that's 2, this 2 and 2 will cancel out. That leaves me with 1.5 times 200. So 1.5 of 200 is 300 Kelvin. So the answer is 300 Kelvin. So that's it. So again, that's how simple you use, that's how simple you apply, that's how simple the combined gas law is. That's how you do problems in the combined gas law. Obviously, there are complications, such as, for example, if the temperature is given in Celsius and you are supposed to calculate the temperature, you cannot do this calculation when you have Celsius or Fahrenheit. You have to convert this to Kelvin. Now, for pressure, you can use anything. You can use ATM here, you can use Pascal, you can use PSI, you can use other units of pressure. It doesn't matter as long as you're consistent, meaning if you're using ATM here and it's also ATM here, that's okay. If you're using liter here and it's liter also here, that's okay. However, if you're using Pascal here and you're using PSI or pounds per square inch, And then here you're using ml, but in this case you're using meter cube. Obviously, one of them has to be converted to the other. The units must be the same, because remember, in this case, the crucial part is cancellation of units. If your units are not going to be the same, then it will not end up with a unit of temperature. So therefore, that's the tip. Temperatures must be converted to Kelvin, and then you have to be you can have any unit of pressure as long as it's consistent in P1 and P2. You can have any unit of volume as long as it's consistent in V1 and V2. Okay, if there is a disparity between the two, you have to do some sort of conversion. Okay, so that's it for the combined gas law.